two masses of m, 4 kg, and m equals to 6 kg are joined together by a string that passes over a pulley. This arrangement is known as Atwood's machine. The masses are held stationary and suddenly released. Determines acceleration of each mass. Intuition tells us that larger mass will start moving downward and a smaller mass will go up. So if we say that the larger mass's acceleration is a, then the other mass's acceleration will also be a. But of course, in the opposite direction. The two accelerations are same because the string cannot be extended. The force on each masses are weight mg and tension T. For smaller masses, since it is accelerating upward, so net force is T minus mg equals to ma. Since the larger mass is accelerating downwards, that is net force equals to mg minus T equals to ma. Equation 2 plus equation 1. So equation 2 plus equation 1. We get mg minus T plus T minus mg equals to ma plus ma. The t's are cancelled out and we have mg minus mg equals to, we take it out the acceleration, that's going to be m plus m, and from here we get the acceleration equals to m minus m over m plus mg. So the acceleration of each mass equals to a equals to fraction of the masses m minus m over m plus m times acceleration due to gravity. We can actually find the tension as well. Place the acceleration in back to equation 1, which is T equals to m, acceleration is m minus m, m plus m, g, plus mg, and we need to simplify, that is m minus m squared over m plus m g, and we would like to make the same denominator, that's m plus m plus m times mg, and we need to simplify m minus m squared over m plus m g plus m plus m squared over m plus m and g. So from here I think since the denominator is same, this to cancel out and we get a tension equals to 2 times m over m plus m times g. That's the tension. In figure 2.52, a block of mass m is connected to a smaller mass m through a string that goes over a pulley. Ignoring friction, find the acceleration of each mass and the tension in the string. The forces are shown. The acceleration must be the same magnitude for both masses, but the larger mass accelerate horizontally and the smaller mass accelerate vertically downward. The free body diagram shows the force on the individual masses, taking each masses separately. So for small masses, as it accelerates downward, then we have mg minus t equals to ma. The large mass accelerating horizontally to the right and without friction. So the net force is just a tension, which is equals to ma. That is equation 2. Adding the two equations, 1 plus 2, we get mg minus t plus t equals to ma plus ma. And t's are cancelled out and we get mg equals to m plus m, and acceleration equals to mg over m plus m. That's the acceleration. We plug in the acceleration into equation 2, which is equals to mg over m plus m, and that gives us mg over m plus m. Method 2, treating the two bodies as one, resulting in a situation shown below. The net horizontal force on the combined mass is gonna be F net equals to m plus m a, and the net forces equals to, here we have a T minus T, and here is plus mg equals to m plus m a. Since the tensions are opposite directions, they cancel out, and we get mg equals to m plus m times a. So acceleration is going to be a equals to mg m plus m. This is the same result as the previous slide. A block of mass 2.5 kg is held on a rough inclined plane, as shown in figure. When released, the block stays in place. The angle of incline is slowly increased, and when the angle becomes slightly larger than 38 degrees, the block begins to slip down the plane. Calculate the coefficient of static friction between the block and inclined plane. The friction force is F, and the normal reaction is R, and the weight is W. The components of the weights are, we can move the vector quantity around. The y component of the weight is adjacent, that's W cosine theta. Since the object is moving parallel to the surface, net force in y component equals to 0, which means R minus W cosine theta equals to 0. That means R equals to W cosine theta. That's our equation 1. Because the block is about to slip, the net force in x component also 0, which means the friction force minus W sine theta equals to 0. That gives us friction equals to W sine theta. Because the block is about to slip, the frictional force is the maximum possible static frictional force, and coefficient of static friction equals to friction force over R, and we plug in the values. Friction force is W sine theta, and R is W cosine theta. W's cancel out, and that gives us tan theta, and the angle is 38 degrees. That gives us 0.78. So the coefficient of static friction between block and inclined plane is 0.78. The angle of incline is increased to 49 degrees. The coefficient of dynamic friction between the block and incline is 0.26. Calculate the force that must be applied to the block along the plane so that it moves up the plane with the acceleration of 1.2 meters per second. Since the object is moving upward, then the dynamic friction actually acting down the slope, and we can move the x component of the weight like this, and the y component still there. The resultant forces are the applied force F upward minus the dynamic friction minus the x component of the weight, which is W sine theta equals to ma. And rearrange F equals to MA plus mg sine theta plus the dynamic friction. Since the object is accelerating upward and net force in vertical component equals to 0, which means R equals to W cosine theta. We plug in dynamic friction equals to coefficient of dynamic friction times W cosine theta. We plug in to the equation plus coefficient of dynamic friction mg cosine theta. Now we need to plug in the values. The mass is 2.5, acceleration is 1.2 plus 2.5 times 9.8 times sine 49 degree plus coefficient of dynamic friction 0.26 times 2.5 times 9.8 times cosine 49 degree, and that gives us 25.67, approximately 26 Newton.